Our second lecture set on the whole notion of dynamics of the Earth is going to take us from seafloor spreading down deep within the Earth to look at the interior. So recall from last time that seafloor spreading was the realization that there is heat rising from below to the surface of the Earth, and it is arising in these central parts of these oceans. We call those places mid-ocean ridges, and they are the sites of where the seas are spreading. The oceans are getting bigger. Several lines of evidence supported it by the 1960s then. Heat flow. These are areas of high heat flow. I'll show you a picture of that in just a second. Lots and lots of earthquakes and lots of volcanoes. And then finally, paleomagnetism, which we'll talk about next time. So if we map heat flow with the warm colors, the darker the warm colors are, the yellow, oranges, reds, dark reds, the more heat flow there is. And you can see it's not scattered randomly across the globe. It is very linear. It is very segregated into specific spots, and those spots are the mid-ocean ridges of the oceans. So these places that we discovered through sonar. Second bit of evidence, if you plot earthquakes, if you put a dot every time there is an earthquake and then collect those, aggregate those on a map, the different colors just represent different strengths or sizes of earthquakes. But for now, just look at the actual occurrence of all those dots. It also is not random. They're not scattered randomly across the globe. There are a few that look like that, but mostly they are these very linear features that, again, are in the same places. So think about that. High heat flow and earthquakes occurring in the same place. There must be some relation. And then next, the distribution of volcanoes. Now, this is a little bit different. These are volcanoes that we could see. And here, the more prominent feature is that they are encircling the Pacific Ocean. It's why the Pacific Ocean got the nickname the Ring of Fire, because of the so many volcanoes here. You do see some in these same mid-ocean ridge areas, but not as many. This isn't to say that they're not there. In fact, they are. They're more abundant, and they would also make these nice linear features. Well, that evidence supported and strongly supported the whole notion of seafloor spreading. Now, to get to the last part of this, to assemble the whole idea of plate tectonics, we needed to look at the Earth's interior, the deep interior. And the science of seismology, the study of the movement of shock waves through the Earth, which we developed in the 1940s as well, largely to find oil, so that we could have more petroleum than the German Nazis to win the war. The study of seismology revealed that, well, the Earth isn't a homogeneous ball. There's many distinct layers, big, thick layers, and these layers have very distinct chemical compositions and properties, and they are consistent around the globe. So a little side jaunt into seismology, although if you want this material, you need to take the other introductory course, Geology 100. This is a record of a seismograph. So an earthquake has happened. If things are going on as normal, meaning there's no shaking of the Earth, the line should be straight. When shock waves arrive, the seismograph records them as these up and down motions, and the higher the motion, the bigger the earthquake. And it turns out that you need to have 3 of these scattered around the globe, and if we have this, we know how fast shock waves travel through materials of different types. We can tell in a matter of seconds now where an earthquake occurred on the map, and then how deep within the Earth it occurred. A little bit more example of some of this. Imagine an earthquake occurred right at the top here, basically the North Pole, and boom, it happens where the star is. It sends shock waves through the Earth. We call them P waves and S waves. And if the Earth were just a single homogeneous ball, they would make nice arced paths all the way through. It turns out that there are places where certain waves don't occur, or certain waves occur later than they should have occurred, or in different places. And it allowed us, these weird different patterns allowed us to map the interior of the Earth. Here's another view. Here we have stick figures representing people, men and women manning seismographs around the globe. And here an earthquake has occurred on the equator, on this side of the Earth, and different waves, P waves, S waves, you don't have to worry about them for this class, are sending out through the Earth. The time and just the occurrence of the different waves, P waves and S waves, at all these different places. Notice some places don't get any at all, some get just some P waves, some get both, and they get them at different times. It allows us to pinpoint where earthquakes occurred and their depth. It also gave us this mapping of the Earth, which gives us this. Here's a cross section through the Earth, a slice that you see, and you see large, big layers through the Earth. But if you magnify the outermost portion, so that's what this little square is here, blown up here, you see several other layers, also distinct, also global, worldwide, and they have unique features themselves. If we look at these layers, here is a schematic diagram of a slice through the Earth. We have several layers. Now I'm going to go through them from the surface of the Earth to the center of the Earth. So the surface of the Earth could be right up here. And first of all, we have what's called continental crust. We live on it. This is the land. If you were to take a generic composition, melt down average rocks around the whole continents, it would be primarily granite, and the density would be about 2.7 grams per cubic centimeter. Now, you don't have to memorize the number. What you're going to have to know is the trend. The numbers up here in the continental crust are going to be lowest, and they're going to get bigger and bigger and bigger as we go down. How do you interpret that? Well, a cubic centimeter is about the size of a sugar cube. It means that, there's sort of 1 centimeter by 1 centimeter by 1 centimeter cube. And if you were to weigh pure water, that is, the weight of that would be 1 gram per cubic centimeter. Well, rocks are heavier than water, and so the numbers are bigger. And granite happens to be about 2.7 grams per cubic centimeter. This behaves in what we call brittle deformation, meaning if you exert a force on it, it breaks. Think about taking a hammer and breaking a rock, or throwing a rock through a glass window. It shatters, it breaks. We call that brittle deformation. There's another type of crust that we call oceanic crust. This is the crust that is not what we're living on, but the bottom of the ocean floor. It is thinner. It is made of a different material. It's made of the rock type basalt, and its density, notice, is a little bit higher. If continental crust was 2.7, oceanic crust is 3, it's heavier. That explains why the oceans are sunk lower. They're the low spots, so they're what gets filled with water. Below the oceanic crust, we have a huge area. So look on the right side here, mantle, 2,900 kilometers from the edge of this dark green pattern way down here to the bottom of this first orange. And this is the mantle. There's a little bit of variety in here, and we'll talk about that in just a second. But its general composition is what we would call peridotite. Its density is a little higher still, 4.5. This behaves in what we call a ductile deformation, meaning if you exert a force upon it, it doesn't break or shatter like brittle. It bends, it flows, it warps, it deforms. A whole bunch of words to describe deformation that is not breaking. Below the mantle, then, we reach an area that is so hot, the outer core, that it is now liquid. It is hot molten magma that is super, super dense, primarily because it is made of iron and nickel. And notice here the density is much higher. So that little sugar cube of rock that we're sampling in all these different layers, the numbers are getting bigger and bigger and bigger. We know that this is a liquid. We've never been down here. We've never even drilled all the way through this green area, this green crustal layer up here. We only know about these layers because of how fast shock waves go through them. The fact that they drastically slow down or, depending on the wave, disappear completely tells us that this outer core is liquid. And then finally we reach the inner core, and it's probably made of the same stuff, but now there is so much pressure on top of it that this iron and nickel that was liquid here in the outer core is now solid again. So there's a solid ball inside a liquid center, and then covered by a ductile material, and then a hard, brittle material at the top. We can look at the slices through the earth in a couple other ways, especially these upper ones. The crusts, both of them, and the uppermost part of the mantle, if we look at how they behave in a physical sense, this is the area of brittle deformation. So lithosphere. These are the places where the earth gets cracked and broken, which makes our earthquakes. Below that lithosphere then is an area that we call the asthenosphere. This is the upper part of the mantle below the lithosphere. The big difference here is that deformation here is mostly ductile. This isn't solid rock, hard rock that breaks when forces are exerted upon it. It deforms in a ductile manner. So think about this. The lithosphere pieces are hard, brittle pieces broken by these earthquakes that are floating on and moving on this slowly deforming, moving mass of asthenosphere.